Page 3 of the HL addendum for applications of differential calculus. If you read on page 617, it talks about the ladder leaning against the wall and maybe sliding down problem. The ladder is 5 meters long. The height at which it hits the wall is y, and the distance from the wall in which it comes in contact with the ground is x. If the ladder starts sliding down, the length of y and x are related. And if you can figure out like how fast it's sliding down vertically, you can figure out how fast it's sliding down horizontally by using a differential equation. Okay, so let's look at that. Let's first of all try to figure out what is the relationship between x and y here. This is a really easy trig problem, right? You can use Pythagorean's theorem and say that x squared plus y squared equals 5 squared, right? So let's do that first. So x squared plus y squared equals 25. And then we can relate the speed with which it is falling down in the y direction to the speed in which it's falling down in the next direction by doing a derivative with respect to a third variable here, which is time, right? Because if we wanted to figure out how fast it's sliding down, that would be like the change in y with respect to time, right? So let's take a implicit derivative of this function with two variables, x and y, with respect to t. And that would give us 2x dx dt plus 2y dy dt equals 0, because the derivative of 25 with respect to anything is 0. Maybe you might eliminate the 2's. You could divide everything by 2 and you wouldn't cause any problems. So x dx dt plus y dy dt equals 0. So at first it says write down the differential equation given to describe the motion of the ladder. That would be exactly this here. It doesn't really explain what a differential equation is, but basically for you guys right now, you're going to learn more about differential equations when we do the green book. But for now, what you can think of it as is it kind of happens when you do an implicit differentiation and you have derivatives mixed in with other variables and you can't really separate them, maybe, like in this case here. Okay? So next step, it says the equation is a related rates problem because one of the variables is time. Okay? So we took a variable which wasn't even in the original equation. The original equation was x squared plus y squared equals 25. There was no time there. We introduced time by taking the derivative of everything in the equation with respect to time. Okay? What are the steps to solve a related rates problem? Okay, the first thing is to draw a diagram. That will help you make this equation, which kind of defines the relationship between everything, which some people find is the hardest thing, although really it doesn't require advanced math to do that part. Write down the info, label the diagram, and distinguish between variables and constants. Okay. You might use Pythagorean's theorem, similar triangles, and proportion, right angle trigonometry, or non-right angle trigonometry to write an equation connecting the variables. So like, that's what we did here, right? Here, we had the variables x and y. We related them by writing a Pythagorean theorem equation. Differentiate the equation with respect to time to obtaining a differential equation. Finally, solve for the particular case, which is some instant in time. Okay? And so, for now, what we're going to be doing is they're going to give us like, oh, what if the speed of the ladder sliding down the wall is 2? What would be the speed of the ladder sliding away from the wall? So you would relate dx to dy dt. They would give us a dy dt, and they would give us enough information to figure out exactly what the derivative is. Nothing complicated. We're not figuring out a function which describes x or y, for example. Okay? We'll do that later in the green book. Okay, a and b are variables related by the equation ab cubed equals 40. At the instant when a equals 5, b is increasing at 1 unit per second. B is increasing at 1 unit per second. That's another way of saying that dB dt is equal to 1 unit per second. What is happening to A at this instant? Okay, so we need an equation which has A in it and dB dt in it. And the way we're going to do that, if you look at our procedure, they already gave us the equation which connects the variables, which is step 3. We need to do step 4, which is to differentiate the equation with respect to t. Okay, so we're just going to do an implicit differentiation on this equation. A times b cubed is a product, so we're going to do product rule. So A times 3b squared dB dt equals 0. Oops. Product rule. So, plus the derivative of A times b cubed. And that equals 0 because the derivative of 40 equals 0. And then they tell us, okay, we want to know, they say what is happening to A. What they really want to know is dA dt. Okay? How are we supposed to figure out dA dt? There's all these variables. Well, they did tell us that A equals 5, so we know this is 5. They did tell us that dB dt equals 1, so this is 1. So all we're really missing is B. Now, how can we figure out B? Well, we have an equation which relates A and B. So since we know that that A is 5, we actually have this equation here. 5b cubed equals 40. One variable, we can figure out what b cubed is. It's 8. B is equal to 2. Okay? So now we can put 2 in here and 2 in here. And so we'll have 5 times 3 times 2 squared times 1 plus dA dt times 8 equals 0. Okay? And so let's simplify this. So we're going to have 4 times 15 is 60 plus 8 dA dt equals 0. And then we're going to have 8 dA dt equals negative 60. dA dt equals negative 60 divided by 8, which is 7.5. Okay? So what is happening to A at this instant? It is increasing, or it's decreasing. It's negative 7.5. It's decreasing by 7.5 units per second. Okay, a ground level floodlight located at 40 meters from the foot of a building shines in the direction of the building. A 2-meter tall person walks directly from the flashlight towards the building at 1 meter per second. How fast is the person's shadow on the building shortening at the instant when the person is 20 meters from the building, or 10 meters from the building? Okay, so we got a floodlight which is shining toward the building. And a person, which is 2 meters tall, is walking from the floodlight toward the building at 1 meter per second. How fast is the person's shadow on the building shortening at the instant when the person is blah, blah, blah? So let's draw a line representing the shadow. So it would go right by the top of the person's head. And it would be that height right there, right? That's how tall the shadow would be. Let's figure out an equation which relates the height of the shadow from the distance to the distance that the person is from the building. Okay, so let's say that the distance that the person is from the building is called x, and then the shadow is called y. Let's see. It looks like it would be some kind of trig relationship, right? I think that we do know that the person's height is 2. This length here looks like it would be important. If we had this length, then we would be able to relate the 2 meter high person to the angle here. So let's name this length here. It would be 40 minus x, right? So if we made a trig relationship between 2 and 40 minus x, it would probably be tangent, right? Because it's opposite over adjacent. So the tangent of, let's call this theta, equals 2 over 40 minus x. And that would give the relationship of the smaller triangle. And then the larger triangle would be tangent of theta equals y divided by 40. Okay. And let's see. We don't really need theta. We don't need theta. So what if we eliminated theta by setting both of these expressions equal to each other? So we have 2 over 40 minus x equals y over 40. And that gives us an equation which relates x to y. So maybe now we could figure everything out. They're giving us this the change in x with respect to time, because they told us that the person is walking toward the building at 1 meter per second. Now, if we're talking about x, so x is getting smaller, so dx dt, basically they're saying, is negative 1 meters per second, because it's getting smaller, okay? So we know dx dt, they're giving us x in two different cases, so we know x. And so we basically just need to figure out what y is in terms of x, which we can with this equation, and we need to know what dy dt is, and that's basically what they want to know. They want to know how much the person's shadow is shortening as he approaches the building. So let's find an expression with dy dt and dx dt in it. We could do an implicit differentiation on this equation. Now, this equation has x in the denominator. That's not like a pleasure to take a quotient rule when you don't have to. So how about if let's cross multiply maybe, and then we'll end up with an expression which doesn't have fractions in it. Because we know implicit differentiation. And so since we know implicit differentiation, we don't care if the variables are mixed up. Sometimes it's easier to take the derivative if we do implicit differentiation, even when they are mixed up. So we'll simplify it a little bit so that we don't have to do product rule either, or at least not any more than necessary. And then now, are we ready to take the derivative? Yeah, so let's take the derivative now. So the left side derivative would be 0. The right, remember, we're taking the derivative with respect to t because it's a related rates problem. So the derivative of 40y is 40 dy dt. The derivative of xy, and we'll factor out the negative sign here, would be dx dt y plus x times dy dt. Okay. So now we have an equation which has the variable that we want, which was we want dy. We want to know what dy dt is, right? And we can figure that out since they gave us dx dt and they give us enough information to figure out what y would be also. Let's collect our dy dt's together. And then we can make an equation which will give us the answer kind of immediately. So we'll combine like terms. So it'll be 40 minus x dy dt minus y dx dt. And also, they don't give us y. So how about if we modify this equation so that y is given in terms of x, which we can do by modifying this equation. So we'll have y by itself on the other side, and then we'll have 80 over 40 minus x as the expression, which puts y in terms of x. And then we're going to substitute that in here. So now we're going to have an equation which is pretty much the way we want it. 40 minus x dy dt minus 80 divided by 40 minus x dx dt. And that's all equal to 0. And now let's try to maybe plug in some of the numbers. that they give us and see if we can get some answers. So what we're looking for, remember, is how the shadow is changing. We know that the derivative of x with respect to t is -1, right? We found that out here. And then we know that x, in case A, we're solving for a particular case. What about at the exact moment that he's 20 meters from the building? What's happening then? So we know that x is 20. So x is 20. So basically we're going to have 40 minus 20, which is 20, y dash, minus, and then we have 80 divided by 40 minus 20, which is 80 divided by 20, which is 4, times -1, and that equals 0. So 20y dash plus 4 equals 0. 20y dash equals -4. Y dash equals negative 0.2. Negative 0.2 meters per second. So at that moment, the shadow is shrinking at negative 0.2 meters per second. And now I'm just going to make a little bit of space because I didn't leave very much space to work on my second case. The second case is when he's 10 meters from the building. So when he's 10 meters from the building, then x is going to be 10 instead. So I'll have 0 equals 40 minus 10, which is 30. And I'll have 80 divided by 40 minus 10, which is 80 divided by 30, which is 8/3. And x dash is -1 because he's always walking at 1 meter per second. So I can just make that into a plus. And now I will do some algebra here. 30y dash equals -8/3. Y dash equals, I'm going to divide both sides by 30, so it'll be -8 divided by 90. And that is equal to -0.889 meters per second. So when he is 10 meters from the building, I'm sorry, it's not 0.889, it's 0.889. So you can see that like his shadow is not shrinking as fast as it was as when he was at 20 meters away from the building.